Physics Notes, Unit 18, Part A, second part of Part A. I'm going to finish this off. Here's the diagram. Once again, you might need to pause this and write this down. So we're calculating Coulomb's law forces, electrostatic forces, and now we're going to be looking at the vector nature of these. Here we have three collinear points. I meant to say that in the problem here. Three collinear points. They're on a line, separated by 20 centimeters and 40 centimeters. 3 microcoulombs, -6, and -9 microcoulombs. Micro is 10 to the -6 once again. So this problem it has a lot of steps. You have to do these in three or four parts. Because Coulomb's law, which is F equal, I'll write it down again. It's the force of attraction or repulsion between two electrical charges separated by a distance, equals K Q sub 1. I'll put them all in the numerator because the K always goes in the numerator anyway. K Q sub 1 times Q sub 2 over the distance between them squared. Alright, so we got to do this 3 times in this problem. And the diagram is very, very important. For example here, I'm going to do these. I'm going to start with the 3 and the 6. So the 3 and the 6 attract each other. So the way I'm going to show that is this. I'm going to put these two arrows so you can see them. I'm going to call that F sub 1. That's F sub 1 and F sub 2. That's an F sub 1 and F sub 2 there, if you can see the subscripts. So that's a F sub 1 and F sub 2. Well, they're equal to each other. So in some sense of the word, I didn't need to subscript them. I could just call it F, but there's a reason why I want to call it F1 and 2. So I'm going to color coordinate this so it makes it a little easier to follow, I hope. So F sub 1 equals F sub 2 equals, I'm going to use Coulomb's law, equals 9 times 10 to the 9th times the product of the two charges, 3 micro. I got to remember on my calculator that that's going to be 3 times 10 to the -6 times 6 micro. Don't need a negative. I've already actually included a negative with those arrows. The arrows are what, the -6 is what, on the +3, they're opposite charges, opposite signs, so they attract. Divided by 0.20 meters squared. Alright? So if you go to your magic box, your calculator, punch all those numbers in. You might need to pause this and you might want to try it yourself first because you need to be able to get these answers correct. 4.1 newtons. Attracting, it's in the diagram. So that's the attractive force between those two. They're pulling equally on each other. Alright, now I'm going to take the -6 and the -9. They repel each other. So I'm going to show that in green. Maybe hopefully green shows up. They repel each other. Alright, so I'm going to put 2 arrows that show that they're repelling. But I'm going to call that F3 and F4. Right, F3 and F4. Now F3 equals F4 once again. F3 equals F4. It's the same format. It's still 9 times 10 to the 9th times 6 microcoulombs. Don't need a negative. Times, oops, I need to put the micro in there though. Don't forget to put the micro in there. So because you got to have that in your calculators. 6 times 10 to the -6th times 9 times 10 to the -6th divided by that distance squared, 0.40 squared. So if you do the math there, once again, plug it in your calculator, the bigger distance tends to reduce the force, but there's a bigger force now which increases. So the net result is, if you do all that math, 3.0 newtons of repelling. So those two charges repel with that magnitude of force. Now we have the two outer forces, the 3 and the 9. Now they're opposites. One positive, one's negative. So they attract each other. Alright, let me go back to red, I guess, or something. Right, so they're going to attract each other. And they're far apart. So I'm going to show you the attraction they have. I'm going to call that F5 and 6. Lack of creativity, but numerically here, that's a F5 over there on the far left, and F6 for the force on that -9 microcoulombs. Once again, 5 and 6 are equal to each other. So I have to move my plate or okay. F5 equals F6 equals 9 times 10 to the 9th times, what do we have? The 3 microcoulombs. Doesn't matter what order you go in here. Times 9 micro. Just got to remember to put that -6, 10 to the -6. Now, be careful. The distance here is 0.60. The total distance is the 40 plus the 20 centimeters is 60 centimeters. 0.60 meters ends up to be 0.7 newtons. Now, the reason why I went to 1 sig fig is because I have to combine these numbers over here are the numbers that have to be added and subtracted. Basically, I'm doing 2 sig figs here. Even though the problem started off with 1 sig fig, you can do this in 2 or 3 sig figs. If you want to do 3 sig figs, you can on this one. But don't go beyond 3 sig figs. I'm just rounding everything off to 2 sig figs, the last one to 1 sig fig, because I'm just going to, when I add these things or subtract them, as you'll see, you're going to be lining up this last decimal place, the 10th place. For example now, I need to find the net force on the 3 microcoulomb charge. So I'm going to say F net for the 3 microcoulomb charge. Well, it's got 2 forces acting on it. F net is going to be F sub 1 plus F sub 5. How do I know it's the 1 and the 5? Well, I look at the diagram. It's being acted on by force 1 and force 5. So really all I have to do is add those. It's going to be 4.1 plus 0.7, right? Equals 4.1 plus 0.7 equals 4.8 newtons. And I have to say to the right. That's the net force. That's the answer for F3. F net 3 micro. It's 4.8 newtons to the right. All right, so I'll circle that one. A little awkward the way I have that, but that F net 3 micro is that force. Let me go back to a different color now. So how about F net for the 6 micro, the -6 micro? Well, that's going to be equal to, you look at the diagram, F2 plus F3. F2 plus F3. F2 is 4.1. F3 is 3.0. So the net force is 7.1 newtons. And that's to the left. That's the net force on the 6 microcoulomb charge. 7.1 newtons to the left. And here's where it gets tricky. You got to rely on your diagram. All right? Because in the last case here, F net -9 microcoulomb charge. I'm leaving off the the C part. It's obvious what I'm talking about here, the -9 microcoulomb charge. I'm putting units in my answer for sure. All right. Now you look at it's F4 and F6, but which one's bigger, F4 or F6? Look at the diagram, look at the answers. F4 is green, it's 3, and F6 is 0.7. So the rule is take the big, if they're in opposite directions, these are easy vectors to add up or subtract. Take the big minus the small. You subtract them. It's going to be F sub 4 minus F sub 6. It's the big one minus the small one. And it's going to be 3.0 minus 0.7. So you see why I just did the 0.7, I think. That gives you 2.3 newtons. And that is to the right. You got to look at the direction of the bigger force. The 4.0 F sub 4, or 3.0 F sub 4 is bigger, so that's the net force on that charge. That's a lot of fun if you like math. I like math. I like doing that kind of problem. It's a vector problem. It's a pretty straightforward vector problem. All right. So that's that one. All right, number 6 here. Hopefully you can see this. Okay. I don't have the diagram here. Let me pause and draw the diagram. Okay. So we have this square configuration of 4 charges. Here we have in the lower right-hand corner the 8 microcoulomb charge, which they're asking you about. And then we have a positive 4, a positive 4, and a negative 4 microcoulombs. Those are all micros. And we want to find the net force on the bottom right corner. So we don't need to find a net force on all 4 of these like the other linear ones. That would be another extra problem to do, which we're not going to do right now. There's a lot of work, and this one's 2-dimensional, not just the 1-dimensional, so it's going to be a little bit more of a vector problem. All right, and you have to do 3 computations once again to start off with. For example, the 8 microcoulomb charge has 3 forces being applied to it, instead of 2 forces like the previous problem. All right, so let's start with the lower left. The 4 on the lower left and the 8 on the lower right, they repel each other. So the way I can show that, is, well, like this. They repel. So this guy repels this guy. I can call that F1 and F2. I really don't need to worry about F2 here. So I can just calculate F1. So F1 is 9 times 10 to the 9th times 4 micro times 8 micro divided by how far apart they are. It says the square has a distance of 0.25 on all sides. It's a square. So it's 0.25 squared. So that force, if you do the math there, comes out to be 4.6 newtons. 4.6 newtons. Now the nice thing about this one is that if you look at the top right, it's also a positive 4 and it's a negative and a positive 8. Same distance, same two forces. And bottom line is those two repel each other with the same force. I could call that F1 as well, or I could just call it F, but it's the same calculation, F1 and F2. And I really would need I could call those all F1. They're all the same size. So both of those are 4.6 newtons. That's nice. There's some symmetry here, and there's some problems like that in the homework where you can skip some steps. And then we have the corner, the -4 and the 8. Now the thing is, this is the 4 and the 8, but they're further apart. So one of the things, and they attract each other. Well, that really doesn't matter too much, but let me draw attraction here. So they attract each other along that diagonal. So those are going to be different. I'm going to call those F3 and F4. I need to know that distance. That distance. So if you have a square, all right, that's 25 on a side. 25. Those are centimeters. 25, 25, and you got to figure out this diagonal. Okay, some of you I know can take the shortcut. There's a right angle there. That's the diagonal of this square. Call it. I'm going to call it. I'll call it D. You call it R. The bottom line is it's 25 squared plus 25 squared equals D squared, or you know if the shortcut is 25 times the square root of 2. However you do that, Pythagorean theorem is the most well, not the straightforward, but it's the most common thing. If you do the math here, it comes out to be 35 centimeters. And once again, the shortcut is it's a 45, 45, 90 triangle, so you take 25 times the square root of 2. You got to get that distance from those two corners, from the upper left corner to the bottom right corner. All right, so now I have that distance. I can calculate F3 and F4. And once again, I really don't care about F3. I could have just called, well, I really don't want to call everything F here because these are different Fs than the other blue ones. So I am using subscripts. But we still have 4 micro. You don't need to worry about the negative. We have that taken care of with the direction of our arrows. So the numerator would be the same as it was before, but the denominator is 0.35 squared. So the force is going to be smaller. It comes out to be, if I do it right, it's about 2.4. 2.4 newtons. All right, give or take a little bit. Hopefully that's close. I think it is. So now I've got to add those three vectors together. I've got to add F1 plus F1 plus F4. But here's the thing. F4 is at a 45-degree angle. What's nice here in this one, here's the shortcut we can do for, you don't have to find the components of F4, which is the way you might have to typically do vectors at angles. Find the components of F4, combine them with the two components of the other two forces. But luckily here, if you use a little thinking, F1 and F1, and this only works if they're equal, because they're equal. So if they're equal, their resultant will be at 45 degrees. In other words, if I take the F1 plus the F1, okay, which are both at 4.6 newtons. Let me draw them in blue just to highlight the fact that they're the blue forces. So I'm dealing with F1. All right. So I'm going to add those two. They're 4.6. That's F1 to the right, and then F1 down, 4.6. So it's easy to add two vectors that are the same size. Famous last words. That's the resulting vector. I'll call it R. And once again, it'd just be 4.6 squared plus 4.6 squared equals R squared. Or you could just multiply by the square root of 2 as your shortcut. So R, the result of adding those two blue vectors, comes out to be hopefully 6.5 if I did it right. So that's the summation of the two blue vectors. Well, if I have, now using some thinking skills here, I have a 6.5 at a 45-degree angle. That's my 6.5 that I just calculated. And then I have F4, which is red, diametrically opposed. So it's easy to add those two kinds of vectors. This only works if they're both at 45, which they both were. That was the 2.4 newtons. That was the F4. So the F4 is the 2.4. So at that corner there, I'm just drawing everything new over here at the right-hand side just to kind of have some space. So you subtract them to get the net force. So the net force is just going to be 6.5. So F net is just going to be 6.5 minus 2.4. You can do that in your head. So F net on the 8 Newton microcoulomb charge is going to be, what, 2.1 newtons? Diagonally out. Diagonally outward. All right, so along the diagonal to kind of give a little bit of a direction, because the 6.5 is bigger, so it's out. The net force is outward for that particular charge. The net force on the other ones is going to be different. I think on the two 4s you'll probably get the same answer. The two positive 4s, you'll get the same size answer on both of those. But on the -4 on the upper left, you're going to get a different answer for that one. So that'd be another good future problem. All right, let's do one more here. Let's keep the ball rolling. All right, let me give you the diagram here. Okay, so we have a 6 microcoulomb and a 4 microcoulomb charge. And we want to know where to put the 2 microcoulomb charge such that it experiences a net force of 0. So here's a thought process. All right, if I put, and this will be the wrong spot, let me just show you. If I put the 2 right here, if I put a 2 coulomb charge right there, 2 microcoulomb, doesn't matter. It's going to be repelled by the 6. Oh, sorry, I meant to put that this is -6. This is -6. So put that in there, sorry. -6. So it's attracted to the -6. So it's attracted to the -6, and it's repelled by the 4. So if I put it anywhere between those two charges, it cannot have a net force of 0 because it has two forces to the left. So that cannot be where you place it, between the two charges. So I'm showing you where the answer can't be. Another place it can't be is over here to the left. So we're thinking of a line. We're thinking of this line. So in my mind, I'll draw the line. I'm thinking of this line because that's what the problem says. Anywhere on this line. If I try to put the, change colors. If I try to put the charge over here, the 2 coulomb charge, 2 microcoulomb charge, the -6 is going to attract, and the 4 is going to repel. So it looks like those could cancel to 0. The only thing is, if you think through this, all right, the attraction arrow, this one to the right, is always going to be larger. It can't be smaller. It's always going to be larger than the other one because, for two reasons, it's closer to the 6, that makes it strong, and the 6 is bigger than the 4. So for two reasons, the leftward force can never match the rightward force. There's no way that those two forces can cancel because the 6 microcoulomb charge will dominate in the application of a force to the 2 microcoulomb. So the 2 microcoulomb charge can't be to the left of that charge. So the only possibility is that the 2 microcoulomb charge can be over here. It can be over here. Okay, it's being repelled by the 4. I'm going to call that F4 in this case. It's being repelled by the 4, and it's being attracted by the 6. Right, it's being attracted by the 6. I'm going to call that F6. That's supposed to be a straight arrow. F6. All right, it's being attracted by the 6, being repelled by the 4. Now those can match up and be equal. And if they're equal, they're going to cancel, because that's what we're trying to do, is try to get those two to cancel. And the reason why they can cancel is the F4 force is large due to location. When you're close to something, you have a large force. But the F6 force is going to be large due to a large 6, as you'll see here. Okay, let me do a little bit better of drawing that. So they can be equal, F6. And I'm going to take some shortcuts here. There's a problem like this in the homework as well. I want F6 to equal F4. We need F6 to be equal to F4 in magnitude. Well, for F6, okay, that's going to be K, Q, 1, Q2 over, I'll call it R1 squared. This is going to be K, Q1, Q2 over R2 squared. This is a generic statement. Okay, because the force, once again, I'm just using the force, F in generic terms, F equals K, Q1, Q2 over R squared. But now let's put some actual numbers in here for F6 and F4. All right, let me go to a different color here. All right, so here's the thing. I'm going to call this distance, I'm going to call that distance x. That's how far I am from the 4 microcoulomb charge. Now I also know that this distance is given as what? Oh, I wasn't given it. You have to be given that number. And it was 22 centimeters. So that wasn't given. I'm giving it to you now. That was in my literature. That should have been written down. So that was given. That has to be given. So that was given to be 22 centimeters. And the charges of -6 and 4 were given. So, okay. Here we go. We're going to plug in. We're going to plug in the specific numbers then relative to those numbers I just put down there. So we're going to have K. So for the 6, it's going to be the 6 microcoulombs times the 2 microcoulombs, right, divided by how far it is from the 6 to the 2. Well, from the 6 to the 2, it's the 0.22 plus x. That's the distance. That could be problematic. Let's find out here. Equals K times, okay, now for the 4, it's the 4 micro times the 2 micro divided by the simple distance there is x squared. All right, so those are all micros in that equation. They're not units. They're not meters or mega. Now, here's the thing. From a mathematical standpoint, there's a lot of things we can do here to make life easier for us. And I'm going to do that for you, because we don't want to do this problem the more difficult way. And that is, first of all, I didn't plug in for k yet because the k's are on both sides of the equation. When there's only multiplication, I know that parentheses on the bottom left. On the bottom left, there's addition here, but that's all in the parentheses, so we can kind of ignore that for the time being. Eventually, we're not going to ignore that. Because if you square that right now, you get a quadratic, and we're trying to avoid quadratics. The other thing that you can notice here, legal move, it's the legal move when there's no addition or subtraction outside the parentheses, is that this 2 microcoulombs cancels that 2 microcoulombs. Additionally, believe it or not, okay, the micro cancels because there's a micro on both sides. So far, you can't just cancel the squares yet because you have to have all 4 of them being squared. But what I've done so far are all legal algebra moves. So what I have here is 6 divided by 0.22 plus x, that's a quantity squared, equals 4. If you wanted to actually multiply all those numbers out with the micros, that'll also give you the same answer. You could still have 6 times 10 to the negative 6 and 4 times 10 to the negative 4, or 4 times 10 to the negative 6, and you'll still get the right answer if you keep those micros in there. And if you didn't cancel out the k's, it'll still work. It's just more work to leave all those in there because they divide out of the problem. In other words, I divided both sides by k. That's what you get rid of the k. I divided both sides by 2 micros. Got rid of those. I divided both sides by micro. Got rid of those. I can't divide both sides by a square. That's not how you get rid of a square. That's why I can't get rid of the square yet. You don't divide by both of those. That's what I've done to get rid of all those things I've crossed out with the blue lines. I've divided both sides by each of those quantities to get rid of those quantities. But how do you get rid of a square? Well, you can apply the distributive property on the left, square the binomial. That's a pain. But here, since it's a fairly simple equation right now, you can just take the square root of both sides. Take the square root of both sides. But when you do that, you got to take the square root of everything. Okay, then I'll bring it over here. I can take the square root of everything. I can take square root of 6. Well, square root of 6, what is the square root of 6? I think I did it earlier. Square root of 6 is 2.45. 2.45. Too bad that wasn't a 9 or something. I thought about putting a 9 there. Once again, I didn't put the negative 6 in there. The negative 6 was taken care of with the directional arrows. So if you put a negative 6 in there, you would have trouble. You can't take a square root of a negative 6. But in the denominator, the square root of that 0.22 plus x quantity squared, square root of that gets rid of that square. So in other words, in the denominator, I have 0.22 plus x. And I can leave that in the parentheses, but I got rid of the square. On the right-hand side of that equation, it's the square root of 4. That is 2. You can put 2.0 if you want. And the square root of x squared is just x. And now life is much simpler for us. Way simpler. I cross-multiply to solve these types of equations. So you get 2.45x equals 2.0 times that parentheses. Normally I would just do that in my head. I'll write it out. 2.22 plus x. I already took the cross multiplication of 2.45 times x. But bottom line here, 2.45x equals 2 times 0.22 is 0.44 plus 2.0x. Subtract the 2.0x from both sides, you get 0.45x equals 0.44. Wow, x equals 0.98 meters. Comes out in meters. 98 centimeters. Almost 1 meter. So you go 1 meter to the right. That's our answer. Where would you put the 2 microcoulomb charge? 0.98 meters. Okay, to be a little bit more explicit, 0.98 meters to the right of the 4 microcoulomb charge. All right, that's how far you are from the oh, I'm sorry. No, that's the right answer. That is the right answer. That's where you have to go to get a net force of 0. And you can go back and plug all the numbers in. You'll find out that the 2 forces will be equal to each other and they will cancel. All right, congratulations. We're done with applications of Coulomb's law, and more on static charges and electric fields coming up next.